should know that one. Example from the PowerPoint. Endothermic and exothermic are good because we also talked about energy. You know, tell me about energy. We have energy is sometimes we call it the total energy. Total energy is sometimes called the internal energy. So tell me about it. See, if I talk about something, then and it doesn't quite make sense, what should you do? What you should do is, if it doesn't make sense, you should ask, you know, at the beginning of the next class, or look it up. You know, if you want to find out right away, look it up online, something like that. You know, but don't let it slide because. You don't want to let things slide. You want to know everything that was discussed, and if it's unimportant, you want to know that it's unimportant and that you could ignore for the test. But you have to be prepared, you know, for everything. So we talked about energy potential. Tell me about potential energy then. What is potential energy?
Like
the maximum energy something can put out. Any other definition? What is that? The charge? Charge arrangement? Okay. Anything else?
Like an example, like compressed air like explode.
Okay, compressed air can expand? Yeah. Okay. Yeah, those are all examples of potential energy. Versus what kind of energy? Kinetic energy. Kinetic energy is like energy that's set in what? Motion. And so like the compressed air, or you know, the potential to do work or the potential to give off energy comes from, you know, things like this. If you're going to store something heavy like this book, you know, in a precarious position, let's say it's just balanced right here, you know, it's got potential energy because it can fall down and hit somebody, but it's not in motion yet. And so in terms of chemical systems, we look at it in the same way. You know, total energy is equal to what? Potential energy. And kinetic energy. And so we look at, when we're looking at things, you know, kinetic energy is easy because what is a direct measure of kinetic energy? I don't want to, you know, actually you should be telling me. I shouldn't. Temperature, right. So kinetic energy is easy. How hot is it? How cold is it? You know, that's easy. So when we look at things, we look, you know, at different things, potential energy and kinetic energy. When I look at anything, so as the examples went for exothermic systems, you know, steam is very hot in terms of energy. So what we do is we just plot energy E going up in some you know, kind of arbitrary scale here. I don't have any numbers to it, but you know, the higher it is, the higher the energy. The same thing happens with what we call gravitational potential energy. When the book is stuck up here, that has high gravitational potential energy, versus if I set the book on the floor, that would have low gravitational potential energy. And so you don't want to put heavy objects up high because the gravitational potential, even though it's not moving, even though the temperature is the same as if it were on the floor, there's no difference in the kinetic energy. The potential energy is quite a bit different. And so here, steam is going to be hot, you know. So that's going to have high potential energy based on its kinetic energy. And then if we go down to water, and we condense it, then this is going to be colder. And so here's a change in kinetic energy. And so when we look at changes, we say delta E. Delta just refers to a change in energy, which is usually E final minus E initial. And in this case, the delta E is going to be either a change in potential energy, delta PdE, and a change in kinetic energy, delta KE. In this case, it's still water. So we start off with H2O, we end up with H2O. So H2O is H2O. And so H2O has the potential to do what? H2O has the potential, you can drink it, you can do other things with it. You know, does H2O burn? No. But H2O will put out fires. And so H2O is H2O. So really the potential energy doesn't change here, you know. There's no change in potential. All the changes in kinetic energy, we just cooled it down, and then we have a lower kinetic energy. Versus other types of things in chemistry, we often look at potential energy quite a lot because, you know, I wanted to dig into this just a little bit deeper because I didn't really touch on this during the talk when I covered this. But tell me about this. Well, we did talk about this. Methane and oxygen, right? Methane and oxygen, this is going to be at 25 degrees C versus CO2 and water. Okay, what do I mean by these? When we're talking about potential energy, we always have to put down the state because, you know, different states will have different energy or kinetic energy or whatever. And so when we're looking at steam, H2O is going to be in the gaseous state. So what we do is we put a little parenthesis subscript G here. And water is going to be in the liquid state, H2O liquid. And so we know H2O liquid versus H2O gas. Well, H2O gas is going to have a higher energy because we got to, what do we have to do to get H2O liquid to go to H2O gas? What was that again? We have to break apart the water molecules because the water molecules are kind of sticky, they're stuck together. What holds the water molecules together? We don't call them bonds, though, per se. The hydrogens and the oxygens, the atoms are held together by the bonds, but two water molecules aren't bonded together, per se, you know, because we think of bonds as being much more difficult to break. And, two water molecules are held together by what? It's related to that. You know, I talk about this. No recall on this one? Look through your notes and see if you have it. Intermolecular forces. And then intermolecular forces, what is the origin of the intermolecular forces? This is kind of the last thing we talked about on Thursday. You have that written? What was the last thing we talked about on Thursday? I'm sorry?
The last thing I have Thursday in my notes is the mass energy equivalent.
Oh, okay. Not the last thing. Before that, sorry. When was the last? Matter? talked about matter, mass conservation, that kind of stuff. What was before that? What do you have in your notes? What was before that?
Electrical charge, polarity.
Electrical charge, right? And so the example, what was the figure? Tell me about the figure that was shown in the PowerPoint. Not the tetrahedral. Tetrahedral, that was related to methane. And we're talking about methane and the structure of methane. So basically what I said was the two water molecules are going to be held together like these two pith balls. You know, they're held together by the electrical forces, right? That's what holds together the two water molecules, electrical forces, which we term intermolecular forces. And these are different than the bonds. Although the bonds are held together by electrical forces, in bonds the forces are just much, much stronger. You know, to vaporize or to boil water only takes 100 degrees C to break, but to break the hydrogens from the oxygen in water is going to take a lot more energy. Heck of a lot more energy to break the hydrogens from the oxygens. Like when you boil the water, the hydrogens and the oxygens are still intact. Water molecules are still intact. They're not broken apart. And so this is just to break apart the kind of the sticky water molecule. So these, I mean, in other words, this is the type of thing you got to review. You got to review because other people are just on it. That's what I found out, because you get a class that half the students are, you know, their goal is to go into medical school, and to get into medical school is not easy. You know, they're very competitive. Actually, my well, anyway. And so you might be surprised. You know, you just have to. You might be surprised at the dropout rate. UCLA is very high. I was surprised as well. But you just have to adapt because the whole curve shifts because of this hybrid. It's very competitive. And so what you want to do is you just want to stay on top of the material. You know, this is like nothing new. Although it might not be totally clear when it's presented, what you should do is before the test, obviously, is to make sure everything's clear. If there's something in the notes that you don't understand, then that's a huge deficit. You know, make sure you understand everything, and if you don't, then make sure you get some help or ask or you know or look it up. Do something to make sure you understand everything. And so this is something I didn't talk about enough. You know, the difference when we're looking at the energies. You know, for example, going from steam to water is going to be exothermic because of the what we call the first law of thermodynamics. The first law of thermodynamics is that energy is neither created nor destroyed. Energy is conserved. So the total energy beginning is equal to the total energy at the end. And so this is what happens. You know, we're starting off with high energy and then we go to low energy water. Well, what happened to all that energy? Well, that energy just doesn't disappear. The energy has to go somewhere. And so in this case, the energy is going to go to, usually, it's going to go to causing burns, which is kinetic energy. I mean, if you touch steam and it condenses on your hand, you're going to feel it because it's going to burn severely because all that energy is being transferred to your skin, which is going to cause your skin atoms and molecules to vibrate rapidly. And so the energy here is going to be released. And it's going to be released into what we call the surroundings. You know, the surroundings are going to get hot. Or they're going to get, the same thing, if we want to boil water, where's that energy going to come from? The energy is going to come from the surroundings. You know, your burner or whatever else you're using to boil water. You're going to input that energy here to jump it up because, you know, energy, like matter, is conserved. In other words, and so this is the way we visualize things. Now, For nuclear reactions, it's a little bit different, and it turns out chemical reactions is a little bit different, but this pretty much is what we observe here. So what can you tell me about these two mixtures? If I have two mixtures, one mixture is methane with oxygen, the other mixture is CO2 and water. They're both at 25 degrees C. What can you tell me about the energy of these two? Well, one thing is, if they're both at 25 degrees C, then they have the same temperature, which means they have the same kinetic energy. Now, to have the same kinetic energy doesn't mean they're moving at the same speed, you know. For example, a big semi-truck versus a little car, to have the same energy, the little car has to be moving much faster than the big semi-truck, you know. It's going to cost a lot more energy to move 5 miles an hour in a semi-truck versus 5 miles an hour in a small car. Right? But nonetheless, we say they have the same kinetic energy because, you know, it's as from Newton's, you know, Newton's laws, you know, yeah, kinetic energy is equal to, this is a very famous equation you might have heard. This is for a single particle, 1/2 mv squared. M is the mass, v is the velocity or speed. And so if something has the same kinetic energy, you know, and different mass, the velocity must be different, basically. But that's a side, you know, if you don't know this. And so, even though the speeds of the molecules and vibrations and whatnot may be different, the kinetic energy is the same. So they both have the same energy.
So what's the origin of the intermolecular forces?
What's the origin of intermolecular forces? What the origin is when we look at a water molecule, the actual molecule like this, it turns out that the molecule of water has a negative charge on the oxygen and positive charge on the hydrogens. And the magnitude of the charge is a little bit of charge, so we call it delta. Delta just means small. Delta minus and delta plus. And so these water molecules have an electrical charge associated with them, so that's why they stick together. They stick together because of the positive being attracted to the negative, just like the pith balls would be attracted to one another with positive and negative. And so what you're doing is, when we're doing it, when we're vaporizing the water, we're breaking them apart from each other. Like here, this is a positive, one of these is positive, the other is negative. You have to pull them apart. To pull them apart, we need 100 degrees C, you know, kinetic energy temperature. Well, these have the same kinetic energy, same temperature, but they are different in energy. How are they different in energy? Potential energy. Which one has higher potential energy? The first one. How do you know? How do you know? Yeah, because you know that methane combusts. So you just had it memorized, probably. You learned it something that, you know, methane's kind of dangerous stuff, right? And it can cause fires and explosions. That's how you. Will CO2 cause fire and explosions? No. I mean, it's still dangerous potentially, but in a different way, health-wise, global warming or whatever. But anyway, okay, so that means that here, this is higher in energy, higher in potential energy. And therefore, when we map this out, we'll say that a mixture of, I need 2 oxygen molecules to react. And so I'm going to start putting in the states. The methane's a gas, oxygen's a gas. And this is a chemical equation. So 1 methane molecule reacts with 2 oxygen. And then we've got to rearrange it because, these ones here, these are called coefficients because we're going to form a CO2. and the hydrogens have to go somewhere, and those are going to form two waters. We saw in the lab the other day. And so here we have our delta, if we start off at 25 degrees C, when we combust it, it gets very hot. But eventually, is that water going to stay hot forever? No, eventually it's going to condense down, release energy. CO2 is also very hot. So wait for that. This is product or reactant here, CO2 and water. We wait for the product mixture to cool back down to room temperature and then figure out how much total energy was released. So delta E is equal to the change in potential energy plus the change in kinetic energy. Was there any change in kinetic energy here? There was no change in kinetic energy. So this is what we call zero here. All the changes in potential energy. So this is a higher potential energy. This is like, gravitational potential energy, like you say here. This would be like this stapler hanging over your head. That would be this potential energy here. This is going to go to much lower potential energy, but we don't call it gravitational. The gravitational potential energy is like this, right? Instead, we call it chemical potential energy. Methane and oxygen has a higher chemical potential energy than water and CO2. It's much more reactive, therefore higher chemical potential energy. I'll abbreviate potential, POTL, potential energy for E. This is lower chemical potential energy, and the changes in chemical potential energy. Something that's higher in chemical potential energy is going to be much more reactive. So we'll just say more reactive. And this is more reactive means more stable or less stable? Less stable. So more reactive, less stable. Whereas something that has a lower chemical potential energy, this would be less reactive, more stable. And so I asked you, what was the example of the endothermic reaction that they gave? Does anybody remember? No? The example they gave is this one. It's going to be CO2 gas plus 6 water versus this C6H12O6 solid plus 6O2 gas. Glucose. So sugar and oxygen, sugar and oxygen versus CO2 and water. Which one has a higher chemical? Well, sugar you can caramelize it, you can burn it, right? Catch on fire. And so that's going to have a higher chemical potential energy. And so in order for us to go from this, let's call this the reactants here, to the products here, we have to input energy. Energy's input back. That would be the example of endothermic. And this example of endothermic was the called photosynthesis. And so here we're going from, normally when we do reactions like this is different. When we heat or cool an object, the object doesn't change. So if you take a piece of gold and you warm it up, eventually it's going to melt, right? But it stays gold. And so this is the way we always think. When we take an object and heat it up or cool it down, we only want the kinetic energy to change. We don't want the potential energy to change. So we don't want it to change from gold to lead or something like that. It just stays gold. You can melt it. You can also try to vaporize it. And so, like water, boiling water, it's adding heat or temperature. When we're dealing with chemical reactions, we want to keep things simple. Obviously the temperature can change, but we wait. We wait until the temperature goes back to its normal temperature. The normal temperature we've chosen is 25 degrees C. 25 degrees C is a little warm. It's like 77 Fahrenheit, something like that. So it's a little warm, but they call that room temperature. My preference is a little cooler room temperature, like a 22, maybe 23. I prefer like 74. 77 is too hot. But anyway, when we do chemical reactions like this, we like to keep the kinetic energy the same. And so we keep the reactant temperature and the product temperature the same and only look at the change in chemical potential energy. This is the way we like to visualize things. So in photosynthesis, the plants are going to get energy from the sun. They're going to take CO2 and water and convert that into glucose or cellulose, oxygen for photosynthesis. These types of things you should insert into your notes. Don't leave them on the PowerPoint. Put them in your notes. That's what you should do.
How does it show the temperature up there on that equation?
It doesn't.
Whenever it doesn't, it's just assumed that.
The temperature. Well, no, you can't assume that. The reason is this is not detailed enough. They're talking in this book. They're talking about kinetic energy and potential energy early. And so what I decided to do for this is, if I'm going to cover kinetic and potential energy, I'm going to talk a little bit more in depth, because what happens is a lot of people go, okay, kinetic and potential is still fuzzy, and it remains fuzzy until they get to Chem 1A, where they have to know it in a lot more detail. And so what I decided to do for this is to talk a lot more about the changes in kinetic and the changes in potential. So this is totally different. Your book doesn't talk about this. The energy input here is what we call delta E. And delta E here, this is going to be a change in potential energy plus a change in kinetic energy. Here the kinetic energy didn't change. And so this energy change here, this gap here, is all in potential energy. So we have to supply that amount of energy to this. Now the supply of energy, this is actually going to come from sunlight. That's going to supply that energy for photosynthesis. In other scenarios, the energy comes from other sources. And so this energy and this energy are actually two different things. This is the energy that's required. Where am I going to get that energy? And in this case, the energy is coming from the sunlight here. Well, I talked about thermodynamics before. What did I say about thermodynamics? Basically, you want a little faster recall for that, if possible. But the recall comes from repetition. The recall doesn't come from having some kind of genius memory. The recall just comes from repetition of seeing it more than once. How many times have you read through and also making sure your notes are complete. As I said, a few things about thermon, and maybe, some of the stuff maybe don't want to bother writing around. How long have the laws of thermodynamics been around? A long time, like what, 10 years?
Way longer.
Way longer? Like hundreds of years? And And what did I say in relation to that length of time?
It hasn't been disproven yet.
Yeah, it hasn't been disproven. Good. So that's good. Although people have tried, right?
Yeah.
Many people have tried. Well, thermodynamics. This is thermodynamics here. Thermodynamics is one of the toughest topics in science. It's what they call a Weeder course at UCLA. At UCLA, thermodynamics. The Weeder. Have you heard of Weeder courses? Weeder courses. They just thin the field. And that was the first course I took at UCLA, thermodynamics. So it wasn't easy. It was very difficult. And so that course. Well, anyway. So thermodynamics, you definitely want to. It's like if you read it once, it's hard to remember. But if you read it like several times, then it makes everything easier to remember. And so you might think, asking me this is ridiculous. That was a long time ago, number one. And number two, was it even important? Do I even need to know it? Well, you're going to be in for a surprise. Yes, you do need to know it because sometimes, Professor will ask you obscure information that they just mentioned in passing. And two, you need to be able to recall it quickly. And to recall it quickly is you got to just drill it in. And it's easy. These are simple drills. It's like simple. When you do exercise, you start off slow and then you build up. But you just don't jump into a marathon. You just slowly build up. That's what happens. You feel like, if you don't study and you don't drill and you don't do this stuff, that's what it feels like when you go in to take a final exam. It feels like, oh my God, you're just in the middle of a marathon. You're not prepared for it. That's the way I felt in thermodynamics. And so what we want to do here, and this is why I'm maybe doing it a little bit more, is thermodynamics is a challenging topic. So let's start off easy and simple and then try to build up from there. Although the book is a little too easy, too simple, so I want to take another step up. Another step up is to talk more about potential energy and kinetic energy in relation to this. And so this is it, where I'm going to leave off. Okay, what else did we talk about? I'm sorry. Chemical change versus physical change. All right, so what's the difference between a chemical change and a physical change? New products? Good. Yeah, well, that boils down to this as well. When we're talking about potential energy, it's a bit tricky because I'm talking about chemical potential energy here, but hot objects also have potential energy. So steam. H2O gas. You would think this would have a higher potential energy than H2O liquid. Especially if this is at 100 degrees C, this is at 25 degrees C. So you go, wow, the steam has a higher potential energy because it could really cause some severe burns. And that totally makes sense. Everybody would know what you're talking about because, yeah, of course, potential for severe burns, third-degree burns with steam. But the weird thing is this. When we're talking about potential energy, yes, but when we're talking about chemical potential energy, then no. The weird thing is both of these have the same chemical potential energy. Why is that?
It's still water.
Because it's still water. So this is kind of related to, these are things you think about. These are things you think about after reviewing and drilling down more and more, and then you go, okay, what's the relationship between chemical changes, physical changes, and chemical potential and kinetic energy? these are the things you think about when you're at a much advanced level, you know? Like I was saying that, you got the people, you know, when you have a very long marathon, people start to spread out, you know? And you got those people who are just on it the whole way. They're gonna be at the leading of the pack, and this is why the curve was so hard to adjust to, but you could be there. It's so easy to be at the head of the pack. That's what I found out. How do you do it? You just, rather than trying to do the whole marathon by jumping into it head first, you build up to it slowly. You build up to it slowly by reviewing your notes every day. You know, if it's not clicking like this, then review it more frequently. Every day from the beginning. But compare with your friends to make sure that you didn't miss anything and they didn't miss anything. You know, that you guys are. And so you just build up. So we talked about physical and chemical changes. And so, you know, this would be physical, chemical. What else did we talk about? You know, I would usually take this a step farther because I go back to day one. You know, what did we talk about day one? Scientific method. Oh, I'm sorry?
I'll just say scientific method.
Oh, scientific method we talked about? Why did we talk about the scientific method that day? What were we discussing? What was the example? Apple from the tree? Okay. Yeah, Newton's, that kind of thing. All right, so what you want to do is you just want to do that so that rather than coming up with maybe being confused or coming up with a blank or having to look back, it comes up and recalls, you know, in your memory. And just build up a little by little here. Well, so we'll continue doing a little bit of this as we go along, but we got to move on as well, otherwise we're not going to cover the new material. So we're going on to chapter 3 for the cover this week. Chapter 3, and this is a short week, so just cover this chapter. This is a very long chapter, though. So, you know, these are the learning objectives, writing scientific notation. So we need scientific notation. We got to use a calculator with scientific notation. We've got to deal with conversion factors. Do you know what a conversion factor is? Yeah? Yes or no? Maybe. But we'll talk about them, so you should know what conversion factors are and how to use those. We'll talk about that. Conversion factors are very important because we use that in our way of solving problems. The number one way of solving problems in chemistry is by dimensional analysis or factor label, you know, which we'll talk about in great detail. A metric system versus English units. Metric prefixes, talk about that. Further, metric prefixes distinguish the difference between mass and weight. Mass and weight are often used interchangeably, especially like chemists, but physicists would never mix these two up. We'll talk about that. The standard units of mass, length, and volume. We do unit conversions. Okay, that's it. So we'll be looking at this kind of long chapter. A lot of learning objectives here. All right, so we'll just start off here. Scientific notation. This is also in the math review, and there's lots of reviews on scientific notation. But you know, what do we call this first part here? Coefficient. And then this part's the exponential. And then the exponent. This is a standard form. It's between a number between 0 and 10, but it doesn't have to be like 9. Sometimes we express it in terms of 100 or something like that. Conversion of decimal number to scientific notation. So let's just do examples of this. You can look. So here we convert 3,672,199 to scientific notation. What would it what happens is we make this number smaller by moving the decimal point. Therefore, the exponent has to grow bigger. And so, how many places do you move this? 1, 2, 3, 4, 5, 6, 6 places. So this would be 3.672199 times 10 to the 6, positive 6, yeah. And so in other words, if this number gets smaller, this is going to get bigger. However, this number here is very small. So this number is going to go big. We're going to go 1, 2, 3. And so it's going to be 4.61 times 10 to the negative 3. So exponent gets small, negative 3. So 4.61 times 10 to the negative 3. And so this is what they're saying. You know. Well, the way I say it is, if this number goes small, the exponent goes big. If this number goes big, the exponent goes small. Essentially, what they're saying here, but I don't remember right and left. So I just remember big, small. So what we're going to do is, if this number is small, then what we're going to do is we're going to convert it to decimal form. When we go to convert it to decimal form, we're going to go to 0. And so we need to convert it to times 10 to the 0th, which is 1. And so what we're going to do is we're going to make the exponent bigger, which means we have to make this number smaller. So to make it smaller, we're going to move this decimal how many places over? 11 places over. And so moving it 11 places over. Just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11 places over, and then we put a 0 in front just to more clearly mark the decimal. 0 point. We need zeros. 4, 8, 10. 10 zeros. So we're going to convert 5.16 times 10 to the 4 to decimal form. This is big. So yeah. So just move to the right. This is a review, right? You guys have this in math. So maybe this is a little too easy. All right. Then, how do you punch it into a calculator? So we're going to use the EE or the EXP key for punching this into the calculator. And so let's get some practice punching this into the calculator. So how would you key this number into your calculator? Tell me the buttons you can put. I push 3.49 EE or EXP, and then what? Negative 11. I don't know why, though. A lot of people use the times 10 to the X key. Have you seen that? The times 10 to the X key. And so let me just show you on the calculator here. use this key here, 10x key. Does anybody use the 10x key for scientific notation? If you do, don't. Stop using it. You should use the EE or the EXP key. What's the difference is you're going to be off by a factor of 10, depending on how you key the number. And so normally I can see people doing it because their answers are off by 1 order of magnitude. Just because when you hit the EE or the EXP key, or some calculators will have this times 10 to the x, then it's okay. This would be okay. Or the EE or the EXP key, I think, EXP, according to the slide. Well, we do, you might not be. It's just, it just depends on how you key it and then the number of steps, keystrokes that you have to do. And so this is using too many keystrokes because you'd have to do times and then this 10 to the x and then enter it. Whereas the EE already does the times 10 to the x. And so this scientific calculator, I don't particularly like. Let me find a different one. I should have looked earlier. Okay, this is it. Here's the double E key. And so you would use this. And so the other key is what we call the anti-log. And so if I'm going to punch in that number, what was it? Let's just do 9.16 times 10 to the, was it 6? Equals 9,160,000 versus, okay, I do 9.16 times, okay, then I'd have to do the inverse law. Well, actually, I was going to show you my calculator. But anyway, be careful with it because it could screw you up. I don't see. Do you see the invert key here? Well, I've seen this times 10 to the 6. So let's try that. So 9,160,000. But doing that takes extra keystrokes, which is going to make you slower. And also there's potential for getting off by an order of magnitude. So these are two different ways. All right, so scientific notation, keying it in. Okay, then what we're going to do is we're going to look at dimensional analysis here. This is the first example of dimensional analysis. When we do things, there's two components to the numbers that we look at. One is just the quantity, like 50. The other is the dimension or the unit. And so whenever we have some quantity, we have to always have a unit and the number itself, so 50 minutes. So express 50 minutes in seconds. And so a lot of people can do that, no problem. But what we're going to do is we're going to do it a little differently in terms of setup. And so this is what they were talking about earlier for the units. dimensional analysis, what we have is the given thing, which is going to be 50 minutes. Okay, the abbreviation for minutes is MIN. And then what we need to do is we need to convert this into seconds at the end. And so we need to convert the dimensions from minutes to seconds. The way we convert the dimensions from minutes to seconds is by using conversion factors. This would be a conversion factor. Ideally, we'd like one conversion factor that does this directly. The one conversion factor that would do it directly would cancel out the minutes and replace them with seconds. And so the conversion factor would be an equivalence, which is multiplying. So for example, here, the conversion factor would be 60 seconds is equivalent to 1 minute. And so what we would do here is we'd write 60 seconds on the top and 1 minute on the bottom. And so the dimensions would change here. And then we just take 50 times 60. Well, 50 times 60 would be what, 300? 300 seconds. So this is the point of dimensional analysis. Dimensional analysis is going to require a conversion factor. This conversion factor is nice because it was direct. It's one conversion factor. Other times, it's going to require multiple conversion factors. And so, one or more required. Now, the way we write this is we write it as a ratio, like this. And so this 60 seconds to 1 minute can be written in two ways. It could be written 60 seconds per minute, like this, or it could be 1 minute per 60 seconds. And they do different things. This one would convert from minutes to seconds, if we're looking at the numerator here, minutes to seconds. This one would convert from seconds to minutes. And so conversion factors are used in that way. And so here, you could see,
Isn't it 3,000 seconds?
oh, 3,000? 3,000 seconds. We got to, actually, I got to double check the answer to make sure it's reasonable, because 60 seconds is 1 minute, so 300 seconds would be what? 180 would be a few 4 minutes or something like that. 5 minutes, 5 minutes, 5 minutes, yeah. And so this would be 50 minutes, which would be a lot bigger. Well, that's the next step we're going to do. We're going to check our answer. So here we see our given and then the dimensions. So first we look at the dimensions and we come up with a conversion factor here. So 50, 60 minutes cancel. So it gives us the 3,000 seconds. Okay, let's look at another one here. Okay, this next one, the oldest horse racing track in the United States is 8 furlong Pleasantation Fairground racetrack in California. What is the length of the racetrack across? Okay, yeah, I don't understand this. We can figure it out anyway. What's given? It's 8 furlong is given. So if we're given 8 furlong, then it doesn't matter if we understand what a furlong is or not. I don't actually know what a furlong is, but I do know that I need to get rid of it. And so this is the strategy in dimensional analysis. If I need to get rid of furlong, then I need something to cancel it out. So furlong needs to be in the denominator of the conversion factor so that furlong cancels out. But I have to relate furlong to something else. And so what can I relate it to? Rod. And so the relationship is 1 rod is equivalent to 0.025 furlong. And so here I would just do 8 divided by 0.025 times 1, but 1 times 8. And then this should give me the number of rods that we're dealing with. So how many does that come out to? It's going to come out to a big number, right? So we're taking one number and dividing it by a very small number, so it should come out to quite a big number. So we just punch it in a calculator, come up with 320 rods. 320 rods. All right, the convergent factors are just equivalencies. They're just relating two quantities. That's what conversion factors are. Conversion factors are equivalencies relating two or more quantities. It doesn't even have to be two. We can relate more than two quantities, representing the same thing, the same property. So that's what we have here. Write equivalencies and conversion factors for the following. 1 day is 24 hours. So what we can do is we can write this as two ratios, depending on what we want in the numerator and what we want in the denominator. And the two ratios would be this. We know the equivalency here. 1 day is equal to 24 hours. So therefore, 1 day per 24 hours or 24 hours per 1 day. Either way. And so this one would cancel out hours and convert it to days. This one would cancel out days and convert it to hours if we have something in the numerator here. Sometimes we flip it upside down because sometimes we want to change the denominator. Now, this is something that we call an exact equivalency or exact conversion factor. I'm going to start calling this an exact conversion factor because how many hours are there in a day? There's exactly 24 hours. That's the definition. Although the days might be getting longer or shorter. But here, this is exact. However, is this exact? My car averages 17 miles per gallon. Does his car or that person's car average exactly 17 miles per gallon? No, that's what we call a non-exact conversion factor. In other words, what we have is we have uncertainty associated with it. Here we have no uncertainty associated with this because everybody knows 24 hours per day. But here, the uncertainty that's associated with it is given by something called significant figures. So the way scientists read these two numbers, even though 24 has two digits and 17 has two digits, right? And so both of these are two-digit numbers. They're treated differently. And so the 24 is exact. However, when we see 17 like this, then in science, the general practice is this. If we see 17, then that number can range from anywhere from 16 and a half, because 16 and a half would round to 17, all the way to 17.4. This is like when we're talking about sterling silver. What did I say about sterling silver? Yeah, right. It depends. Is sterling silver exactly, what was it, 98% silver? Was that it? Is exact? It would be nice because if it were exactly 98%, 98 or 92% silver, then each time you got sterling silver, you're getting exactly the same amount, But what that is, it's not exact, And if it's not exact, what do they mean by 92? Well, what they mean by 92 is anywhere between 91, I said this earlier, but now I'm going to relate it to this. Anywhere between 91 and a half and 92.4. I got to double check the number because I don't remember the exact number. It was just a point. I think it was 92, right? That means it's anywhere from 91.5% to 92.4%. That would qualify as 92% because this one would round to 92, that one would round to 92. So both of these are legally 92%, right? But you're getting different amounts of silver, especially if you're getting tons of silver. If you're getting tons of silver, then that's a huge difference in amount of silver, right? Huge difference. And so I'm sure that the makers of sterling silver always give you this, right? The low end, because it's going to save cost. I'm sure that's it. I really doubt a maker of sterling silver is going to give you this but this is the uncertainty that's associated with non-exact numbers, non-exact numbers. So when we have conversion factors like this, these equivalencies, we think, is it exact or not? This one's exact, yes. This one's not. Now let me ask you, 60 seconds per minute, is that exact or not exact? Exact. Now 0.025 furlongs per, or what was it, rod per rod, is that exact or not exact? We don't know. It depends. That could be exact. It depends. Usually if something's exact, it was by definition. So if somebody said, I would think this is exact because, you know, it seems like
40
that.
rods per furlong.
Yeah, it seems like it would be exact. But sometimes it's hard to tell. This one's easy to tell. I mean, it's an average, so it's not exact. And so, you know, somebody said that, but the range could be different, you know. If it averages 17 miles per gallon, then typically we take that as this kind of uncertainty, but, you know, it could be a much huger range. If it's a much huger range, then we indicate that range by using something called error bars. Oh, I totally forgot about the, I guess we're still okay. Forgot about the break. Huh. What time do we end at? 1:05? 12:35? 12:50 today? Do you want to leave early or do you want to take a break now? Take a break? All right, we'll take a break. Let's take a break now.